Hello everyone. Hello sir. My name is Pranab Nandi. I'm from MTech CSC. Today my seminar topic is Proportional Integral Controller Queue Management Algorithm. Let's see the index page of our seminar. First we will see what is network congestion and the effect of network congestion. Then we will see the congestion control technique and the congestion avoidance techniques, followed by the importance of queue in routers. After that we will jump into the queue management technique like passive queue management technique and active queue management technique. After that we will see the proportional integral controller, we will see its algorithms and its implementation, and finally we will see the validation of PI controller in NS3 network simulator. So let's begin with the network congestion. In computer network the resources are limited. If you talk about the router processing time or router buffer or the link throughput. So when a node or a link is carrying more data than it can handle, then there will be a congestion in the network. For example, in the given image, if you see this particular router, for this router the incoming packet rate is 10 Mbps and the outgoing packet rate is 1.5 Mbps. So it is quite obvious that it is not possible for this router to send all the packet that it is receiving from this site, from this node, from this link. So some packets will be stored in the router buffer and that packets will be sent to the outgoing link after a certain time. But the thing is that this buffer size is limited. So after a certain time the buffer will get full and the router will start dropping the packet. So this is the typical effect of this congestion. Also, as the router is dropping the packet when the buffer is full, it will also drop the TCP SYN packet, which is useful when a new node try to establish a connection with another node. So directly or indirectly it is blocking the establishment of new connections also. There are some network protocol that use the aggressive retransmission to compensate for the packet loss that occurs due to congestion, also increases the congestion more and more. So to control the congestion we have to come up with some algorithms like congestion control algorithm and congestion avoidance algorithm. In case of congestion control algorithm, what we try to do, we try to stop the congestion when there is nothing in the network, there is no congestion in the network. But when you realize like there is congestion in the network, we try to avoid it with the help of congestion avoidance algorithm. Some devices already implemented some of these algorithms. For example, exponential backoff in protocols such as CSMS-CA, which is there in the Wi-Fi, and also similar kind of CSMS-CD, carrier sensing multiple access carrier detection, in the original Ethernet is already implemented. Window reduction in TCP control the congestion to some extent. And most importantly, the queue management technique in devices such as routers and network switches play an important role in this network congestion circumstances. So what is queue in the router? As I already mentioned, in router there is something known as buffer, and it is really useful when the incoming rate is more than the outgoing rate. But I also mentioned like the buffer size is limited and after a certain time when the buffer is full it drops the packet. So the question is like, though we know nowadays the memory is quite cheaper than olden days, so why don't we keep the router buffer size very large? If we keep the buffer size very large, then it will increase the queuing delay of the packets which are there in the router buffer, and which will result in the buffer bloat problem. So for that we can't keep the buffer size very large. So we have to keep the buffer size in a limited value. But the thing is that with this limited buffer we have to control the congestion also. So to deal with congestion we have to come up with some queue management algorithm that can efficiently manage that router buffer, because in internet we have different set of applications which demand defined requirement. If we talk about the application like bulk file transfer, that means while we are downloading a 5 GB files, it demand high output, whereas the time sensitive application like Google search demand ultra low latency. On the other hand, if you talk about the multimedia application like watching some videos in YouTube, it demands consistent performance. That means lesser variation in the delay. So you can see the router buffer or the queue has to fulfill all the requirement, but its size is also limited. So we have to manage this queue effectively and intelligently, and for that we have some queue management technique. These are passive queue management technique and the active queue management technique. So let's see what is passive queue management technique. Though there are many passive queue management technique, but the two most important passive queue management technique is drop trail technique and the drop font technique. In case of drop trail technique, what happens when the incoming packet is more than the outgoing packet, as I already mentioned, like it will be stored in the router buffer. When the buffer gets full, the packet will be dropped from the tail side. You can see that it is dropping from the tail side, whereas in case of drop font technique, the packet will get dropped from the font side. But these are the static queue management technique. It does not consider the dynamic changes of the network, so it is not that much useful to manage the queue effectively and efficiently. So for that we have another set of algorithms which are known as active queue management algorithms. It is really useful to manage the queue efficiently and effectively. Some algorithms includes like random early detection, random exponential marking, followed by modified REM, then blue and stochastic fair blue, then the PI controller, proportional integral controller, then we have rate with preferential dropping. After that we will have control delay and robust random early detection. In this seminar we mainly focus on the proportional integral controller. As I already mentioned, like packet usually dropped by the router when the buffer is full, but the PI controller drop the packets before the buffer is full. And how it drops the packet? It drops the packet based on some probability which is known as the dropping probability or drop probability, and this drop probability usually a function of instantaneous queue length. So PI controller does not randomly drop the packet, it drops it probabilistically. Sometimes it does not drop a packet, rather it marks the packet. What is meant by marking a packet? It usually set the ECN bit of the packet to inform the sender that probably there will be a congestion in the network, or there is already congestion in the network. The PI controller is inspired from the closed loop control system. Basically, the closed loop control system usually used in a variety of applications that requires the continuously modulated control. It calculates the error value, which is ET, by taking the difference between the set point and the process value. After calculating the error value, it sends this error value to the two components of the system. One is proportional and the second one is the integral. Hence the name came proportional integral controller. After that it calculates the UT, which is nothing but the manipulated value with this equation, where the Kp is the proportional gain, which is a tuning parameter, and the Ki is the the integral gain, which is also a tuning parameter. After calculating the UT, it will feed this value to the plant or the process that we are trying to control. So from that concept we come up with a linearized AQM control system, which has two part. The first part is CS, which is the main controller, and the second part is the PS into E power S R0, which is the TCP AQM that we are trying to control. You can see in the second diagram, this is the implementation of PI controller, where this Q0 represents the set point or the Q reference value or the desired queue length, and Q is the process value or the current queue length of the present sample, and delta Q is the difference between these two, which will then sent to the PI controller. After that, PI controller calculates some value. This value is fed to the AQM dynamic system. The PI controller has its transfer function, which is written in this equation. Here the KPI stand for the proportional integral constant, and the KPI is defined by this equation, whereas in this equation R stand for the round trip time, C stand for the link capacity, and N stand for the the number of TCP connection. The PI controller calculates the drop probability at a sampling frequency represented by W, and it is calculated through this equation. So in this equation, the Q length represents the current Q length, the Q reference represents the desired Q length, Q old represents the Q length during the previous sample, and P old represents the drop probability during the previous sample. We'll say that the Q reaches a steady state when this particular term will become 0. In that case, the P will be equal to P old. This means the drop probability of the current sample will be equal to the drop probability of the previous sample. This is the implementation of PI controller. Here, this is the base class. The Q discipline is the base class. It has some virtual methods, and we inherit this base class in the Q discipline class. We're gonna implement, and it implements all the virtual methods. Along with it has some new methods, and it has some member variables. After implementing the PI controller, we try to validate it in NS3 network simulator. For that, we use the dumbbell topology, and here the bottleneck buffer size is 200 packets, and the Q reference value is a 50 packet, and the TCP used is the TCP new Reno. The bottleneck bandwidth is a 10 Mbps, and we also use the TCP window scaling. First, we perform the experiment in the light TCP traffic, where we use 5 TCP flow, which are sent from 5 sources at the same time and arrive at the bottleneck routers in a burst fashion. And because of that, you can see a sharp increase in the Q length in the initial few seconds, and after that it can able to come to the standard value. It can able to maintain the standard value. So because of this sharp increase in the Q length, you can see a sudden drop in the throughput, and after that it can able to achieve the pretty good throughput with the light TCP traffic. After this, we perform the experiment with heavy TCP traffic, where we used the 50 TCP flows from 50 different sources, and all are sent at the same time and all arrived in the bottleneck routers in a burst fashion. And because of that, you can see for quite few seconds there is a sudden increase in the Q length, and after a certain time it can able to maintain its Q length to the standard value. And because of that, for initial seconds there is a sudden drop in the link throughput, and after that we can able to achieve a pretty good link throughput. And finally, we perform the experiment with both this mix of TCP and UDP traffic. Here we use 5 TCP traffic along with 5 TCP flow, and along with that we use 2 UDP flows. Each UDP flows is configured to send data at a rate of 10 Mbps. Here, what we can see from the diagram, the PI controller fails to control the Q length in the presence of unresponsive traffic. Because it cannot able to come to the standard Q length, it always maintain the peak value. So from this discussion, we can see that PI controller is a pretty good controller for Q management, though it does not able to perform good with the unresponsive traffic, but moreover the overall performance is pretty good. This PIC controller is not present in the you know traffic layer of the Linux kernel, and also it is not present in the traffic layer of NS3 network simulator. It is under review, and I hope like in future it will merge in the main line of NS3 network simulator. These are the references I used to design the PPT. Thank you.